Hello and welcome to Lecture 9 for the course ECE 1B Freshman Seminar, Spring 2020. For this spring, this will be the last lecture for the course, given that one of the scheduled lectures coincides with the Memorial Day observance. There is a 10th lecture that I will record and post later on for those of you who might be interested to pursue it on your own, but that won't be a required part of the course for this quarter. So this will be the last lecture for spring 2020. Once you have listened to this and submitted your attendance report, you'll be done. If you have 0 or 1 absence, you'll get a pass for the course. If you have 2 absences after this lecture, then you need to contact me to schedule an oral final exam, likely through Zoom. And if you have 3 or more absences, unfortunately, you will not pass the course. And that's according to the grading scheme announced at the beginning of the quarter. Now, today's topic is sorting networks. These are some interesting circuits in computer engineering that we can relate to train sorting puzzles. So we begin with train sorting puzzles and then proceed to relate the puzzles to sorting networks and their applications and design techniques. Okay, before we start with train sorting puzzles, we need to know a little bit about trains, and not all of these things about trains are common knowledge, so I need to review them a little bit so that we understand how these puzzles work and be able to develop solutions for them. So a train is basically a transportation device that moves on a pair of parallel tracks. Now, if you have just a pair of parallel tracks, there isn't much the train can do. In this picture, you see the engine is pulling a bunch of cars, and once it gets to the destination at the other side of the track, the only thing it can do is just to go back over the same track, and this time pushing the cars. So an engine can pull the cars or push the cars. Although we prefer that the engine pull the cars, because then the operator sitting in the engine can see the front of the train and basically recognize any possible obstacles or hazards on the way. But if needed, the engine can push the cars. And of course, these days with cameras, like backup cameras in cars, they can put cameras on the other side of the train so that the engineer basically can see what's in front or actually behind the train as it moves back. Okay, so it can go just back and forth. Nothing exciting can happen. The train tracks are steel, made of steel, and the wheels of the engine and train cars are also made of steel. So they basically roll over the tracks, and they're held in place by some edge to the wheels that hold the wheels in place so that they don't slide off the track. Okay, because these are made of metal, the friction is very little, and therefore an engine can pull dozens or sometimes even hundreds of cars without any problem. By contrast, in cars, the wheels have purposely are made to have a lot of friction with the road so that the car remains stable, doesn't slide uh, to the side, or the wheels don't slide in place, and therefore waste energy. Here we try to minimize the friction in order to make the engine expend as little energy as possible while pulling or pushing the train. Okay, now the first thing that we introduced to this very simple parallel tracks is the notion of a siding or a side track. So here you see in this diagram over here that as a train approaches this branching point, this Y point, the train operator would see this arrow that says if you go further from this point, your train will go on this, in this direction, will go on this side track. So typically this may be the main track. This is a station there. And this is a side track where the train can go and park, unload passengers, load new passengers, and then move on, while leaving the main track open for any passing trains, such as freight trains that don't need to stop at this station. So the train will go. Notice that there is a gap between these two rails. So the wheel of the train basically goes in this direction. And similarly, the other wheel will go there. And therefore, the train will move into that side track. Notice there is another branching point further ahead. And the train at that point can go either to the right or straight. There may be many of these parallel tracks in case multiple trains have to park in that station. Now this is old technology. This is a manual lever. So an operator should come and push this lever in order to change the status of this exchange. So basically, if the lever is pushed to the left, now this arrow that the train operator sees indicates that the train will go straight ahead. So for a short while, this switch is placed in this state so that the train can move to the side, and then it is pushed, the lever is pushed so that this goes to this normal state so that the main track. So basically, when this lever is pushed, this piece of rail over here moves to the right, and therefore this gap disappears, and the wheel of the train will go on that track. And similarly, a gap is introduced there so that the other wheel of the train also can go between the gaps, and therefore the train moves in this direction. Okay, so this is basically a Y interchange with a lever, mechanical lever. These days, all of these are electronic, so that remotely we can change the state of this interchange. And then perhaps some LED display will tell the train operator in which direction the train will go. This is the mechanism by which train cars are connected to each other, or an engine gets connected to train cars. Each train car has this mechanism at both ends, because train cars can be connected to each other at both ends. And then when you push two train cars against each other, those two mechanisms basically engage. Of course, they won't stay in place, because if you pull them back, that thing will slide out. So a U-shaped pin can be placed in these two holes. a U-shaped pin will go into these holes so that these two parts will stay in place, and if you pull this car, it will pull with it the other car. Or if this is the engine will pull that. So it's very easy to connect the cars and to each other and the engine to cars. Simply push them against each other and just manually insert this U-shape pin to hold those things in place. And then once you want to disengage, you just remove that U-shape pin and just pull the cars apart, and they come undone. Okay, as I mentioned before, an engine can push a string of cars or pull a desired subset by decoupling them from the rest. So if this engine suddenly needs to pull just this one car to some destination and doesn't need the other car, so perhaps the train does not have enough passengers for two cars, so we disconnect these two cars using the mechanism I just mentioned, and the engine just pulls the one car and the other car will stay behind. On the other hand, if we want to increase the length of the train, we somehow bring a third car, push it against the second car, and then put the U-shaped pin in so that they get connected. So this is a busy train station with a lot of side tracks, sidings, where trains can park and be loaded and unloaded. So if you have a freight train and it arrives at this station, it sometimes takes days to unload the entire load of the train or put new load on it so that it can pull it to a new destination. So that's why you need so many different sidings, because each train can occupy it for days at a time. And of course, there's a main track someplace where all of these sidings are connected to that main track. Okay, so let's start with this introduction. Let's start with some train rearrangement puzzles. Of course, if I want to draw puzzles with trains on them, it would be nice if I could draw the tracks like this so that they look realistic. But that introduces a lot of work in drawing a lot of tracks. So I just draw the tracks with just one line, which is understood there are really two rails. And there are these wooden parts that connect the rails together, okay? So for simplicity in drawing, the track is represented as just one line. Engine, I typically show in a dark color, and train cars, I use lighter colors so that I can name them if needed. I show the front and back of the car, although many train cars don't have a front and back, they're symmetric. So, either side can be viewed as front or back. But I do show the front because that sort of indicates the direction of movement too. So the engine also has front and back. Okay, so sorting a train means basically putting its cars in some pre-agreed order. So for example, in alphabetical order in this example. So here I have a train whose cars from front to back are C, D, A, B. And I want them to appear in the order A, B, C, D. I want them to be sorted alphabetically. Of course, if all I have is just one track, I can't do that, okay? I can't make a car jump over another one. And in fact, if this car needs repair and needs to be taken out, I can't do that. Okay, so in train operations, we have various aids for doing these things. One of those aids is what is called a stub or lead. So a stub or lead is a piece of rail that connects to the main track as shown here. And of course there's a switch here that allows a train approaching this point to either go into the stub or continue on the main track. Of course, a train coming from this direction, from left to right, just doesn't care about that exchange. It just goes straight. So this exchange is basically one directional. You can go into that stub approaching this point from right to left, or you can go straight, but going from left to right, the only option is just to go straight. So that's a stub. So how can I use this stub to sort this train? Okay, think about it. Remember that the engine can pull the cars. It can pull a subset of the cars. For example, the train operator can decide for the engine to pull just C and D, but not A and B. So we disconnect the train at this point, and the engine can then pull C and D. So how can I sort this particular train? Remember, sorting in this case means just take A and B from the end of the train and put them in front. Okay? Think about this before advancing the video and see if you can do that. Here is my solution. Basically, the train operator takes C and D forward past this interchange and then pushes C and D by changing the state of the switch, goes backwards, pushes C and D into the stub. So now I have D and C in the stub. Then the engine goes back, connects itself to A and B, brings them forward, again past this interchange, and then moves them into the stub. So in the stub, I have now D, C, B, A. So the train is ordered. So the engine just reconnects A and B to C and D and just pulls the entire train out, which is now in sorted order. So what is a general algorithm? In this case, I was lucky because I just needed 2 steps. I just needed to take C and D forward, put them in the stub, take A and B forward, push them into the stub, connect them to C and D, and go out. Okay, so this is not the worst case of sorting. If this C were A, for example, so if I had A, D, C, B, then the task would have been more difficult. So think about this again for a couple of minutes before advancing and see if this arrangement, just having a stub as shown, enough for sorting any train, no matter what initial order the cars are in. Is it true that I can sort the train using this stub? Okay, so I'm going to provide the answer now. The answer is yes. So basically what I have to do is to assemble the train in the stub in the order that I want, beginning with its last car. So in this case, the last car is D, so I disconnect at this point, push D in there. So D, which is the last car, is now in this stub. I told you, imagine that this is A. So I have A, C, B. Now come back and reconnect A to C, but disconnect C from B, pull the train forward and push C into the stub. So what I'm trying to do is to assemble the train in the stub beginning with its last car in the sorted order that I want. Then C will be the next to the last, then B will be the next to the last, then A, and then I pull it up. So no matter what the initial order of the train, I can sort it with just this one stub. although it takes a lot of doing, a lot of pulling forward, pushing back, and so on, but it's doable. Now this stub or lead is a stack in computer science and engineering terminology, or a last in, first out, because the last car to go into the stub is always the first car to be. So the cars that went into the stub beforehand are stuck behind the last car that I put in, and I can't pull those out. What I can pull out first is the last car I put in. So that's why it's called the last in, first out structure, or data structure in the case of computer science. Okay, so the sorting algorithm assembles a train in the stub beginning with the last car. So this basically shows putting D in, then C in, and so on. Now this is another form of stub or lead. It goes in the other direction. So a train going from left to right can go into the stub, or it can go straight, but the train going from right to left basically ignores the stub. It always goes. Now in this case, if the engine is in front of the train, I'm in trouble, because if the engine tries to pull cars into the stub, it will get stuck behind those cars and can't get out. And therefore, it can't use the stub the way I suggested up there to sort the train. However, if I'm allowed to put the engine behind the cars, then a similar algorithm can be used to sort the train. Okay, now again, I want to sort the train into the stub, but this time beginning with the first car. Okay, so here's what I do. I push the train to the right, put it here, and then disconnect C and D. So C and D will remain there while the engine with A and B goes back. Then the engine pushes A and B into the stub. Remember, I tried to assemble the train in the stub, but beginning with the first car. So A is sitting here, B is sitting here. Then the engine goes back, gets C and D, comes back to the left, and goes in to the stub with C and D, reconnects C and D to A and B, pulls them out, and then continues on its way with the cars in sorted order. Okay, this is also a last in, first out structure. The last thing to go in is the first thing that comes out. Now, a siding is basically sort of a combination of those two types of stubs. It can do the job of both because it's connected to the main track at both ends. Because of this connection here, I can use it like this siding. And because of this connection, I can use it like that siding. So it's more flexible. Now this is essentially not only can act as first in, first out, last in, first out as a stack, but also as a queue, which is known as FIFO, first in, first out. So if I push things into the siding and pull them out from the other side, this will be first in, first out. The first thing to go into the siding is the first thing to come out from the other side. Okay, so I don't know if you have ever taken the train into Goleta. This is the Goleta train station, Amtrak station. It's right next to 101 to the north of Hollister, just before Fairview Avenue. So you see in this aerial photo the 101, the Kyrial, and this is the train station. It has the main track and a siding that you see here. It's more visible here. So this is the main track. This is the platform, station platform. And the siding goes on the other side of the platform. So when a train comes, it goes into the siding. It sort of allows people to disembark and embark on the train, and then the train leaves and joins the main track on the other side of the station. There is a parking lot there where passengers and people picking them up or dropping them off can park. Of course, many of you have seen model railroads. They can be very elaborate. In this case, you see this model railroad has tracks. It has interchanges like the one we talked about before, of various kinds. It has repair shops where cars can be pushed in and repaired if needed. And there is something new here called a turntable. So a turntable allows for you to put a car on and then turn it to align with any of those tracks so that the car can go into this repair station, that repair station, that repair station, this track, into that garage or whatever that is. And also it can allow the car or engine to turn around. So it goes in facing this building here, but then the turntable turns and the car or engine leaves from the other side. Okay, so a turntable can reverse the direction of a car or engine and can also serve as a switching mechanism to allow a car to go on multiple tracks on each side. Okay, other things that one sees in some train stations are turnaround loops. This allows the entire, with the turntable, you have to turn the train around one car at a time. The turnaround loop allows the train to turn around no matter how long it is, provided it fits inside this turnaround loop. Because if the loop is not long enough, the train goes in there and the head of the train comes here while the tail of the train is still here. So if the entire train fits in this loop, then it can turn around and go in the opposite direction. Okay, and then we have a mechanism called Y. It's a piece of track vertical to the main track, and then it has two connections to the main track. And this is also a mechanism that you can use to rearrange cars. So for example, suppose here's a car DBAC. Here's the initial order of the cars. And I want to sort them so that A is right behind the engine, B is right behind that, and so on. So here I've shown after the first few steps, the sorting process. So the engine basically brings D forward. So disconnects D from the train, brings it forward, takes it to the other side, and pushes it into the Y. So D goes there. Then it brings B, takes it to the other side, and then pushes it into the Y. It brings A, actually it can bring B and A together, and then leave A in the middle there, and then pull B to the other side and push it in to reduce the number of back and forth movements. So this is now the current state. D and B has been pushed into the stem of the Y. A is sitting here, C is sitting here. And I'm going to ask you to complete as question 1 the sorting process. The objective is for the engine to pull the train to the right with the cars being in the order A, B, C, D. Okay, so complete this sorting process. Okay, this is again an example of a turntable for a model train. Okay, one of the things that we need to do, especially with freight trains, is to deliver the cars to various destinations. So typically modern freight train cars have containers on them. So in order to basically simplify the shipping, a complete container is put on one of these cars, and that container must be delivered to, in this case, we have 3 destinations. So these are factories or warehouses. And car A with its container must be delivered to this factory. So once it's delivered, the factory personnel can take their time unloading it and perhaps loading it with new stuff so that the engine can come back at some future time and take it away to the new. So basically factories have container cars on this siding, and then a new container car arrives, they unload it, they load it with new stuff, and then the engine comes back and takes it to whatever destination it's headed. So now the objective in this puzzle is that we have this train with its cars arranged in order ABC. Car A must be delivered here, car B must be delivered here, and car C must be left here. Okay? Notice that if the engine tries to pull car A into the siding, it can't leave it there because it will be stuck behind car A. So that's why it's a puzzle. We have to figure out a way to deliver car A onto the siding without the engine being stuck behind. Okay, so here's my solution. Think about it. Uh, it needs some doing, several steps, so that each car, A ends up here, B ends up there, and C ends up there. So here's my solution that I'm going to reveal. The train pulls cars A and B. Car C is detached and left in place. Cars A and B are pulled forward. B is left here. Eventually it will be delivered into the siding. A is left there. And now the engine detaches itself from A, goes into the siding, and emerges on this side, connecting itself between A and B. Okay, so now we have the train, car A, car A, engine, car B. Now the engine, while pulling car A, pushes B into that siding, detaches it, and comes back, and then goes on the main track, now pulling car A backwards, okay? Then it pushes car A into the siding, detaches it, and then comes back, pulls car C, and then puts car C here, and then it can either go to some other destination or go back to where it came from, having delivered all 3 cars to the destination. Notice that the engine had to go back and forth between these points. Now, if you imagine that these 3 destinations are not close to each other, maybe there are tens of miles away, this is very wasteful. In order to deliver car A into this stub, the engine had to go many, many miles and come back in order to be able to do that. Okay? So arranging the train in the appropriate order before it leaves the station is advisable. So perhaps we could have put the engine between car A and B at the source train station, so that when it arrived here, it could push A into the stop and just continue. So it just had to make one pass to deliver all the stuff. Okay, perhaps we could put therefore A in front of the train and B at the end of the train, so that B can be pushed there and C can be taken. So that's why ordering the cars of the train may be important to make the deliveries more efficient. Okay, now this is the toughest puzzle from the set that we consider today. It's called the train passing puzzle. Okay, it's an artificially constructed puzzle. It's not something that happens in practice, but it's interesting. So we have a main track and a siding that is very small. It can hold only one car or one engine. If you try to put two cars in this siding, it's too small to hold them, and the cars will stick out from the ends, therefore blocking the main track. You can only put one car in the siding without blocking the main track and still be able to use the main track. So there are two trains, the green train going from right to left. It can have an arbitrary number of cars. I've shown just two, but it can have 100 cars. Okay, the yellow-orange train going from left to right. So the dark colored boxes are the engines. Our objective is to allow the two trains to pass each other so that the green train continues on the track and then the yellow-orange train also continues on the track to the other side, having passed each other. And I have only this siding to work with, which holds only one car. Okay, this is a challenging puzzle. Okay, so I challenge you, encourage you to think about this before advancing the video and seeing my solution. Surprisingly, the problem can be solved. No matter how long the two trains are, they can pass each other using, that single car siding. Here's what we do. The brown engine detaches itself from its train, puts itself in the siding, and allows the green train to pass to the other side. Then the brown engine goes to the right, and from that point on, the brown engine doesn't do anything. It just sits there waiting for its cars to come. The green engine does all of the work. So what does it do? The green engine pulls the A car, so detach A from the rest of the train, pulls the car into the siding, and emerges from the other side. So leaves the car A in the siding. And then goes to the other side and pushes A out while pulling B into the siding. So pulls B into the siding, pushes A out all the way to the engine. A gets connected to its engine. And again, this green train will go while B is in the siding. The green train will go to the other side and push B. And this process continues, and you can do it no matter how many cars there are in each train. Basically, you push the brown engine to the right and leave it there, and the green train takes the cars from the other train one at a time, pulls them into the siding, goes to the other side, pulls the next car into the siding while pushing this one out, and repeats this process until all the cars of this train have been pushed to the other side, and then it can continue on its way, and the other train can continue on its way. Okay, so question 2 asks you to analyze this solution method. If the left and right trains have L and R cars respectively, how many times will the siding be used for the trains to pass? Basically, how many steps do I need to do this? If I have L cars in the left train, in this case the yellow-orange train, and R cars in the right train, the green train. How many times do I need to use the siding? So the answer, of course, will be a function of L and R, which you have to come up with. Okay, now this type of rearrangement and combining of cars into trains is something that is done all the time. So we need, we don't want to have puzzles. So we want to have an easy way to do this. In fact, it's very common, say, for a long freight train to go into a station, be divided into smaller trains and go to various minor destinations. This is sort of like, distributing the mail. A huge truck or a large plane carries the mail between cities. Then once that truck or train goes, or plane gets to the big city like Los Angeles, smaller trucks will take the mail headed from that city to smaller cities, Santa Barbara, uh, and so on. So one of the things we need to do is to be able to break trains into smaller trains, compose larger trains from smaller trains, and basically you rearrange. So we do this very often, so we need efficient mechanisms. So here's one example of an efficient mechanism. Somewhere in the station you have multiple sidings that allow you to quickly rearrange a train or decompose it. So for example, if I want to sort this train so that A is at the beginning, okay, I push D into this siding, I push B into this siding, I push A to the other side, then I push C into the siding where B was, then the engine goes to the other side, pulls B and C together, and then, or pushes B and C, doesn't matter, depending on whether we want the engine to end up pushing the train or pulling the train. We can do that. Okay, so this is efficient because we have multiple sidings. We can also have multiple stubs, and the same principle applies. So I want the engine to pull A first, so I push C into the siding. I push A into the siding. I push B into the same siding where C was because B and C are already in order there. Then I push D into another siding, and then I pull them out in the order that I want. Pull A out, then pull B and C out, then pull D out. In fact, in order to avoid the need for this engine to keep going back and forth, usually this area is built so that it has a slight slope, so that if you leave a car there and do not apply its brakes, the car moves basically backwards. And then by setting, if you want C to go into this stub, you set the switch here appropriately, release the brake of the car, and the car basically, using the force of gravity, will move backwards and go into that stub. Then disengage A from the train, release its brake, and then set the switches appropriately so that it now goes into this stub, and so on. So the engine does not have to go back and forth because the gravity does the job, and it's much faster. And of course uses less energy too. Okay, question 3 that I want you to answer is to sort the two trains shown at the top of this slide. Okay, both in the case of 3 sidings and in the case of 5 stubs. Okay, assume that I'm using gravity. In other words, there is a slope. The cars can go in on their own once released, and their brakes are released. Once disengaged and their brakes are released. And similarly, there is a slope here that if you just leave a car on its own, it will go into one of these sidings depending on the switch setting here. Okay. Now, the connection to sorting networks. So imagine that I have 4 parallel tracks as shown here, tracks 1 to 4, and 4 cars or 4 trains. These can be trains, they don't have to be cars. And the numbering of the cars tell me which track they should end up at. So this is a mechanism I've built to allow me to put this car on track 3, this car on track 1, this car on track 2, and this red car on track 4. So there are 2 kinds of mechanisms at play in this diagram. One is unconditional exchange. In other words, 2 cars approaching this exchange, they simply switch tracks. The car on the top track goes on the bottom track. The car on the bottom track goes on the top track. So this is unconditional exchange. I also have something called conditional exchange or compare exchange. So if 2 cars approach here, suppose car 4 is here and car 3 is here. They're out of order because I want the cars to be ordered on the right side. Car 1 should be here, car 2, car 3, car 4. Whenever they are out of order, I allow them to exchange tracks. Otherwise, they just move straight ahead without exchanging tracks. So this is conditional exchange based on the numbers that I see on the cars or trains. So let me use this mechanism. The cars move forward. This is a conditional exchange. 2 and 4 are out of order, so they do exchange there. 1 and 3 are in order, so no exchange occurs here. So this is after the first 2 exchanges. Actually, 1 exchange and 1 no exchange. Then we move forward. 1 and 4 unconditionally switch tracks. Then again, I have 2 conditional exchanges. 1 and 2 are out of order. 3 and 4 are out of order. There. And then they're already sorted, so I'm in trouble. So this mechanism is not correct because now 3 will unconditionally go on track 2 and 2 will go on track 3. So I was not successful in sorting using the mechanism that you see here. Okay, now instead of actually switching tracks as shown there, I can draw the tracks as straight lines. This is an easier way to draw that diagram. And then because this track goes up there and there's a conditional exchange between these 2 tracks, had I kept this track in place, the exchange should have occurred between track 1 and track 3. So that conditional exchange is now here. And this conditional exchange between track 2 and track 4 is shown here. So rather than move the tracks around, the tracks are kept as straight horizontal lines. The exchanges are drawn to connect to appropriate tracks. Again, let's do this. So there is conditional exchange between 2 and 4 and between 1 and 3. After these two conditional exchanges, 1 and 2 are compared, and 3 and 4 are compared. So this network that I've shown there can be represented in simplified form by what we call a stick diagram. So basically, tracks are always horizontal. They never move from the horizontal place. Exchanges, conditional exchanges, are shown as sticks between these two, between these two, between these two, between these two. So this is what I have there so far, but the train is not properly sorted yet, okay? So I'm going to insert one more conditional exchange there and in the stick diagram, okay? So now 2 and 3, which are out of order, will be ordered, okay? So my claim is that this particular arrangement of tracks and conditional exchanges is always adequate to sort 4 trains. Of course, I need to prove this. It worked for this particular initial arrangement, but there's no guarantee that it will work in all cases, okay? So how do I validate this? So this is a sorting network. A, B, C, D come in, some unsorted arrangement of the numbers A, B, C, D. And then I expect the smallest one to go on track 1, the next smallest on track 2, and so on. So why is this a valid sorting network? Okay, I can analyze this and say that, okay, after the first conditional exchange, the smaller of A and B will go to the top, and the larger of A and B goes to the bottom. Similarly, the other exchange, the smaller of C and D and the larger C and D will go as shown. Then this next exchange up here takes the smaller of A and B and compares it against the smaller of C and D. Therefore, the smallest overall will end up there. And similarly, the largest overall, the largest of A and B is compared against the larger of C and D. So this will be the largest overall. And these other two, whatever order they have, they will be properly ordered by that last conditional exchange. Okay. Now, in this case, the sorting network was small enough so that I could do basically a mathematical analysis and prove that it's always adequate to sort a set of trains, or in the context of sorting network, a set of values coming in. So this may be viewed as a piece of hardware. I input to it 4 numbers, and it outputs the 4 numbers for me in sorted order. Okay, it's called a sorting network. In stick diagram, that sorting network is shown here. The 2 exchanges here are these 2 short sticks. The 2 exchanges here between 1 and 3 and 2 and 4 are here, 1 and 3 and 2 and 4, and this last one is that. Now these diagrams are much easier to draw, therefore we like these, because in fact I don't even have to draw those dots because there's no ambiguity. You know, any stick is connected to the lines at its 2 ends. So this stick is connected to the lines at its 2 ends. Now imagine if I wanted to show that this is a correct 16 input sorting network. It's not as easy to prove, okay? Therefore, we need a mechanism, a procedure for being able to prove that such a sorting network is correct, and more importantly, to design the sorting network in the first place. How did the designer of the sorting network decide where to put these comparators or exchange elements. It's non-trivial. But even if this is given to us, and we are just asked to verify that it's a correct sorting network, it's a non-trivial task. Basically, if you have 16 inputs, the inputs can arrive in any of 16 factorial possible orders. And 16 factorial is a huge number. I have to basically test this network for each of those 16 factorial cases to make sure it works in all cases. So how would we establish this? This is hard. We have something called the 0-1 principle. What is the 0-1 principle? The 0-1 principle says a sorting network built of comparators is valid if it correctly sorts all 0-1 sequences. So if I want to verify a 4-input sorting network, I apply to it all possible 0-1 inputs, and there are 16 such possibilities. And if it works for all these 16 possibilities, so beginning with 0, 0, 0, 0, 0, 0, 0, 1, which is 1 in binary, 0, 0, 1, 0, 2 in binary, all the way to 1, 1, 1, 1, which is 15 in binary, and just trace the operation. So for example, in this case, 1 and 0 are out of order, so I would get 0, 1. This 1 and 0 are out of order, I get 0, 1. So I now have 0, 1, 0, 1. 0, 0 are compared, nothing happens. 1 and 1 are compared, nothing happens. So I still have 0, 1, 0, 1. This 1 and 0 will be ordered, and I get the sorted order. So if I verify these 16 cases, I can certify that this is a correct 4-input sorting network. So it's basically 2 to the n instead of n factorial. So it simplifies my, of course, 2 to the 4 is 16, and 4 factorial is 24, so there isn't much saving here. But if n were 12, 2 to the n is 4096, whereas n factorial is 479 million and change. So it really simplifies the task because I need to apply 4096 tests to that 12-input sorting network. And going back to the example in the previous slide, the difference is even larger. 2 to the 16, okay, so 2 to the 16 is 16 times 4,000 versus 16 factorial, which is an even larger number than 12 factorial. Okay, so how did anybody come up with the idea of that 16-input sorting network? Well, here is what they actually did for that particular example. So basically, the designer said, let's sort collections of 4 inputs. So the top 4 inputs are sorted by that 4-input sorting network. The next 4 are sorted. The next 4 are sorted. So these are 4-input sorting network, which we already know are correct. And therefore, we use those design. Then we design what is known as a 4-4 merger. So we have a 4-input sorted sequence. A 4-input sorted sequence. This is a merging network. And there are methods for designing merging networks. I won't discuss them here, but there are very elegant methods for that. So here I now have 8 of the inputs sorted. First sort these 4 and sort these 4, then merge them. Similarly, merge these 4 and these 4. So I now have 8 inputs, 8 of the inputs sorted here and 8 of the inputs sorted here. And now I need a merging network for 8 and 8 inputs. And this is the design of that merging network. Again, as I said, we have procedures for building these. So that's how that 16 input sorting network came about. It was systematically designed from 4 input sorting networks that were combined with 4-4 merger network to get, so this part is an 8 input sorting network. And then 2 8 input sorting network, their outputs merged, gives me a 16 input sorting network. Okay, this is one of the most fascinating discussions in computer architecture. In fact, I have a discussion of sorting networks in my parallel processing graduate course where we discuss these methods and the theories behind them. So here is an example. So a set of inputs shown there. After we sort them using the 4 input sorting networks, I get 5, 8, 10, 12. Here I get 2, 6, 7, 14. Here I get 1, 4, 9, 11. Sorry, 1, 4, 9, 15. And then 0, 3, 11, 13. Then I merge these two. And finally, I merge the two subsequences of length 8, and I've sorted the numbers. Now, because of this structure, now if I didn't know anything about the structure and I wanted to sort the 16 input sorting to verify, even with the 0-1 principle, I would need 2 to the 16 tests to verify. That's still a large number. But because of this structure, I need to test each of these 4 input sorting networks. Once I build them, I apply basically 5 inputs. Okay, so once I've sorted that, I need to sort this 4-4 merger. And the 4-4 merger basically needs only 25 tests because it's guaranteed to have these 4 inputs sorted, and it's guaranteed to have these 4 inputs sorted. So a sorted 0-1 sequence of size 4 can have only 5 possible values. Okay, 4 zeros, 0001, 0011, 0111, and 1111. There are 5 possibilities for a sorted sequence of length 4 consisting of zeros and ones. So for each of these inputs, I applied those 5 possibilities. That's why I have 25 tests there. And then 81 tests for this network. Because there are 8 inputs that are sorted, so there are 9 possibilities, beginning with all zeros, ending at all ones. So this is basically, a little bit over 100 tests compared with 2 to 16 tests, even with the 0-1 principle. Okay, there are various ways of building sorting networks. So this is basically using what is known as insertion sort. Basically sort n-1 of the inputs. So it's a recursive solution. Given n inputs, sort n-1 of them, a smaller problem, and then merge the last one with that sorted sequence. These comparators do the merging. Compare with the largest one, move it up. If that one is larger, move it down. Compare with the next one, move it up if needed, and it may move all the way. If this happens to be the smallest, it will move all the way up. Otherwise, it will just settle in the correct place. This is selection sort. Basically, select the largest value among the inputs by these comparisons. What is the larger of these two? Compare that against the third one, find the larger. Compare against the fourth one, So the largest one basically sinks down and goes here. That's the largest. And now sort n-1. Now both of these recursive structures lead to this network. So insertion sort and selection sort, when repeated, lead to this. Notice that for selection sort, we have this ladder-like structure there. This is it. And then this is the rest, the n-1 input sorting network. And here I have this ladder-like structure at the end, and this is an n-1 input sorting network. This is not a particularly efficient way of constructing sorting network, but it's interesting that, we do have very simple, easy to understand methods for designing sorting network. I call this the brick wall sorter because it's sort of, the drawing looks like a brick wall. And this is not efficient because the cost is proportional to the square of n, and the delay is proportional to n. And cost times delay, which is often taken to be a figure of merit, is order n cube. It's a poor design in these respects. So this is just a numerical example. I won't go through, and it shows that the numbers will be sorted. So the best sorting networks, you can define them in two ways. First, criterion one, the number of sticks or compare exchange blocks. So each compare exchange block is a simple electronic circuit. So the fewer of those you use, the better, the lower the cost. So these two examples, both of them being 10 input sorting networks, have costs that are 29 and 31. And therefore the one on the left is better, more efficient with regard to cost. Criterion 2 is the delay, the number of compare exchanges that are done in sequence. And when you count delay, it's kind of tricky because you see all of these comparators that are encircled, they count as 1 unit of delay because they do comparisons between different lines. So they're doing their work in parallel. So this is line 1 and line 5. This is line 3 and line 7, and so on. So their functioning does not depend on each other. So they count as just 1 unit of delay. So that counting is rather tricky. But assuming that I can do that, I can count and conclude that the circuit on the right has a delay of 7, and the circuit on the left has a delay of 9. Therefore, that higher cost circuit is faster. So if I'm interested to see whether the trade-off is worthwhile, I can multiply the delay and cost and get 261 for the circuit on the left and 217 for the circuit on the right. So the cost delay product is better, which was sort of obvious because I shaved 2 units from the delay while adding only 2 comparators. So it's a worthwhile trade-off. Okay, so we have electronic sorting networks that use 2 input comparators. So A and B come in. So imagine A and B are, say, integers. They come into this box. The smaller of the 2 emerges on the top output, and the larger of the 2 emerges on the bottom output. And if I put 4 or 5 of these boxes together, I can build a 4-input sorting network. And of course, as I mentioned in the case of train tracks, instead of switching these lines, I draw the lines straight through, and this comparator, instead of comparing between line 1 and 2, will do between 1 and 3, which was the original position of that. Okay, so this is a 4-input sorting network in stick diagram format, and this is a 4-input sorting network in block diagram format. And we prefer the stick diagram because it's much easier to draw. Applications of sorting network include directing information packets to the destination in the network router. So in the internet, the routers receive many packets that are headed to different destinations and have to quickly decide where to send each packet. The packets are coming at a high rate, and therefore the decision has to be fairly quick. So sorting the packets by their destination addresses is one way to reduce the latency of that decision. So network routers may have these sorting networks built in to help with routing. Also, connecting end processors to end memory modules in a parallel computer. So the processors sitting on one side want to access memory modules. So this processor wants to access memory module 3, this one memory module 2, this one memory module 1, this one memory module 4, and those accesses have to be routed to the appropriate memory modules. And if this pattern here is a permutation of 1, 2, 3, 4, sorting them basically sends each memory access request to its appropriate memory module. So the final question for this lecture is this. In the stick diagram of a force sorter on the top right, I'm referring to this. Show that removing the top or bottom line and its comparators yields a valid tree sorter. So in other words, if I remove this line, the top line, and all the comparators, of course, that are connected to it, because those are useless now, or if I remove this bottom line and the comparators connected, show that what remains is a valid tree sorter. This is actually a more general statement. No matter what sorting network I give you, removing the top line or the bottom line and their associated comparators always results in a valid n-1 sort. However, that's generally not true for the other lines. So here I'm also asking you to show that I remove this line, the second line, or the third line, one of the middle lines, and the comparator. So if I remove this line and the comparators connected to it, this one, and this one, then the result is not a valid tree sorter. So I can get a valid tree sorter from this by removing the bottom line or the top line, but not by removing this line or this line, the middle lines. Okay, that's all I wanted to say about sorting networks. Remember that this is the last lecture for the quarter, and I will be recording the 10th lecture just for the sake of completeness and posting it, although you are not required to view it or answer any questions. When you are done with the 4 questions of this lecture, you are done with the course. All right, thank you, and stay healthy, and I hope the rest of the quarter goes well for you. I hope to see you in person in some future quarter. Bye.